Talk about now is WPC's cluster analysis that they've started looking at over the past 4 or 5 years. And what basically it is now with 50 members ensemble from the European, 30 from I believe from the US GFES, and there will be more. And then the Canadian, there's about 100 uh, individual members. And data overload, as we know, is like you see the spaghetti diagram. If you really don't know what your people are looking at, your eyes kind of glaze over. So what this technique is using a ensemble empirical orthogonal functions and to try to find clusters or a group of members that are similar to each other, so it helps you determine uh, likely outcomes. It can maybe, there'll be one that may be major, then there goes, oh, but this is also could happen. And so I'm just going to show the technique of how how this works and how they do it. And this is really for your days, probably more, it says 3 through 7, but they started out at days 8 through 10 to look at signals. I would say this is really to help you look out for a significant event in the extended range. Here are the references I used. A few papers and the tools, some presentations by the folks. So that if you want to dig into this deeper, this is if you love statistics and you love differential equations, you'll love this. So let's look at the outline. We're going to look at what is cluster analysis. We'll look at the tools that WPC uses, including those empirical orthogonal functions, and we'll talk about principal components of those. 500 millibar EFO patterns, the cluster space. Then talk about how would you go about to identify forecast scenarios. And then we'll talk about a 500 millibar height, QPF clusters, a max min temperature clusters, and really what these, if you'll notice these values from the EOFs and PCs are positive and negative, and what do they really mean? And then how to choose your domain. So what is a cluster? What is WP's cluster analysis? Like I said, it's just grouping the similar ensemble members into a few forecast scenarios that you can use to determine and try to help you figure out what the actual forecast is going to be. And you can also use this to when you're giving your uncertainty or certainty on a condition in your decision support. It also eliminates some of this data overload as I talked. And ensemble clustering isn't new. And if you do some Google search, scholarly Google search and stuff like that, you'll see a lot of other techniques that people are using this for, even non-meteorologically. Let's look at the cluster analysis tool, the EOFs and the PCs. The empirical orthogonal function is also used to study the possible spatial modes or patterns of variability and how they change with time. Tim mentioned the North Atlantic Oscillation. This is where they use how they can come up with this. They examine a time series of anomalies over domain, which is the North Atlantic Ocean, and one can statistically determine the leading spatial modes or patterns of variability. These modes are called EOFs, and the greatest amount of variability is, you'll note, will be in a number 1 group of possible conditions that could happen. The spatial patterns that are more similar are increasingly positive in this, and the ones that are more negative are also dissimilar. WPC, though, because the NAO is done over a time series, instead of using a time series, WPC looks at like the variability of the geopotential height at 500 millibars, but not with time, but over with the different ensembles. So they use what's called a fuzzy clustering to create the clusters. I love that, of ensemble members from the GFS, the Canadian, and the European ensembles, and there are approximately 100 members for days 3 through 7. They calculate, interpret the first 2 of the EOFs, the highest variability to the lowest is where you go 1 through. You can make these 7 or 8 of these, but they have found out the first 2 usually give the greatest differentiation for these different clusters. They use a k-mean clustering to create these clusters. I just talk about k-means follows a simple procedure of just classifying a given data set into a number of clusters. If you want to go into the k-mean, there's a lot of resources available for you to get into that in depth. What they found is the dominant patterns in the cluster can be found by calculating, like I said, only the first two EOS. The first one is always the greatest percentage of spread in the 500 millibar field. The second is the greatest percentage, so forth and so on. Generally, two patterns are seen from this process, and what those processes, if we looked, was we have a dipole, which is two high variability, and this is a dipole showing the possibility of this ridge, or you could do it even with the trough here about the location of where this trough is going to be. If you see a monopole, like if we had not these two, but if we had like this one center that was up here in the ridge, and that would pretty much tell you how deep that ridge or trough is going to be. The example on the bottom right is actually from a East Coast storm, and it just shows you the variability there of its location. Now, there's a thing called cluster phase space, and it's this diagram, and what it does, it breaks these into the principal components. One, along the x have positive to negative values, and a principal component two. Remember, one has the greatest variability, two has the second greatest variability. The way INSEP or WPC draws these up compared to what you see in the literature is they assign numbers to these. And you can see here that the phase diagram forecast scenarios from the first two, the colors represent these different models: Canadian, European, and the GFS. We can also see that the ensemble mean for the Canadian is this red dot, the blue dot is the European, and the green dot is the GFS. Notice how the Canadian European mean is pretty similar, but if we look at what the deterministic, that's what the star represents, we notice that the Canadian slightly positive on the PC1, but what it's showing here, the green, let's say the deterministic of the GFS, it's actually in the secondary variability of that model is more positive, but it's not very close to the PC1. Notice it's negative. So the GFS probably would follow that. Now, when it does these clusters, it puts them into four different solutions, what it thinks the four different patterns might be like. And if you notice, when we get down to one, you'll see this 1, 2, 3, 4. So those numbers represent the cluster number that we're going to see. If you notice here, the green, we see GFS, there's a lot of 4s in green, but then we also see that there's a few Europeans. And when we see these, you'll see it'll help you tell, there will be something in the graph that will show you the percentage of each one. Now, let's identify a forecast scenario, excuse me, and a forecast time of interest. And you can see there is a day 3 cluster prototype page, which we'll go to at the end of this, and I'll show you how it works and how you can find it. And it identifies the region that best, what you want to do is identify a region that best captures the event you're looking for. Let's say there's going to be a big west coast storm coming in that could impact and build a ridge and warm air over the eastern part of the United States. So we use these EFO patterns to identify these regions, and then we confirm the relationship of these EOF ensembles in our cluster space, and we'll look at the 500 millibar clusters. Easy for me to say, you'd say. So what we're going to do here is we'll look at these in a minute. So we're looking at day 6. These are when they predict the variance, it's always on the 500 millibar heights. And here was November 24th. of 2021. I pulled this off the other day. And it's actually ending 0Z last night. I don't know. We'll see how well this did from a week ago. But what we're seeing as the first EOF is the one that shows the greatest variability is the value in the left. And the percentage of the variance between all the models is 40.5%. If we go down to the second or the next most variable scenario, we can see they're showing 21%. And what the difference is there's going to be, all it's telling us, it's not saying the ridge is going to be stronger, but that the values of the ensemble are higher here in heights over Wisconsin and the upper Mississippi Valley. But the second choice that you could come up with is that the heights maybe will be a little higher over the Carolinas and Eastern Kentucky, Tennessee, and West Virginia. Just showing you what the two scenarios could be. Now, if I look over here on the right on the phase space to see how everything lays out, okay, I'm going to start looking at, okay, let's see where all the European are. There's 50 members, remember? So I see a bunch of ones here, right there. Now, if you notice, most of the ones here are in the positive over in the PC1 and the positive for the phase 2. That just shows you most of these members are close to being very similar to each other that it has decided for that cluster. You can see, and down here you see, and we'll go opposite of 4, which is showing that it's more dissimilar than the other ones in version 4. Now, you're going to say, well, where are these clusters that we can see? What we do is we'll change over, and let's look at the 500 millibar actual heights and anomalies for this time. And here are the 4 clusters, 1, 2, 3, 4. 1, 2, 3, 4. And this is the ensemble mean and how you're looking at that. Now, the algorithm always produces 4 of these, and there's good agreement ensembles. So look back at the EOFs to see how much variability is, and we saw there was 40% in this number 1. And we noticed that what we can see from the top is that cluster 1, there's 32% of the members, which is real easy because there's 100 members. So there's 32% of those members in 1. In this cluster 2, we see that there's 28%, cluster 3, there's 22, and cluster 4 is 18. Now, one thing when I go back to this, and notice when you start seeing a model all coming to one solution instead of in 4 different solutions, the model's undispersed. And when you see that, you just pretty much got to say, well, I don't, I would be very, very skeptical of that. So you have to watch that. And that does happen at certain times. Like the GFS all have one similar solution. It's the same model physics and boundary layer and physics all going into the same model. So they tend to converge in some solutions. And you can see there, notice in the bottom right, you notice this always totals 100. So let's look at the 500 millibar heights, the anomalies and what they're about. The anomalies are relative to climatology for each of the 4 clusters, and they all member mean. So this is based on climatology. Where's that climatology come from for the 500 millibar heights? It's based on the climate forecast system reanalysis. When this was written is 1980 to 2010. I saw the current one is 87 to 2017. I don't have any information if it's using the new stuff. I need to ask Jim Nelson on that. But they can change that. That's what this is based off, that climatological mean for your anomalies. When we go into QPF clusters, this is day 7. What we will see is that the cluster mean, QPF, and anomalies are relatively an all member mean. There is no real good climatology for QPF, and there's also problems that some of the climatology doesn't cover the whole US. So what they had to do is make it all relative to the member mean values of the QPF. That's why you see the mean value not having any colors here. And note the shading is relative to this mean value. So one of the important points is just because brown, which is drier, there's still possibility it could be rain. It's just less than the ensemble mean. So there you have to be careful. There could be some impactful events that happen in some of the brown areas. So you have to just really interpret that closely. So let's look at the maximum min temperatures. Yes, they are relative to the all member mean, similar. We don't have a 30-year average on those. And the color shading is relative to the mean. And so you can see how those, and let's look at cluster one. We see it's, there's more, this is more, this does not really say that this is going to be warmer or this is going to be colder. This is just telling you the temperatures in this mean are a little bit are higher than the average. It's very, very subtle difference there. We can see here the 28, we can see they're lower, the mean is lower, and so forth. Oh, and I got a problem with my, let's go back. Hang on a second. I apologize here. I'll just go ahead and run this, even though it's messed up here. Remember that the total positive and negative values in these anomalies are purely from statistical calculations, and they have no physical meaning. It only takes you the meaning on where to begin to interpret it. The other thing is to say choosing domains, it's a big deal. Notice that we have this domain here, the CONUS. Down on the bottom left is the eastern area, central and west. When it does the calculations, it will only do what's in the domain. So if you have a big storm, let's say we look at what's over here, like in the Carolinas, look at this influence of this Pacific system out here is playing havoc with the positive and negative values over our area. So the best thing to do when you get down to more specifics is you can switch it to the eastern domain to get a better idea. Remember clusters at 500 millibar heights? That's what they're based on. So any mesoscale features you may see in the QPF or the maximum temperatures may just be coincidental because the clusters are not based off those fields. And the other thing is no calibration is associated with this ensemble system. Resolution and biases can at times be seen, particularly when one ensemble is going all in. That means, let's say, all 30 of GFS are fitting into this central cluster here. So you have to be really careful with that. So what I want to do next, I know that's kind of something we all have to learn to use. And what I want to do is show you where it's at. If you go to the Ensemble resources, it's actually linked several places, but it's also on the model under the references. And if you go down here to medium range, you'll see the WPC 3 to 7 day cluster prototype page. Now, a lot of this information I got, if you forget how it works, right here, you click on that. It's a great paper by Rutz, Stoudemire, and these other fellows, and it will pretty much take you through similar parts of how this works. I found out this is very, very, very helpful in trying to do this. Now we can go back to the version with the capable to loop 3 to 7 days, and we'll click on that. And the first thing what you want to do is you want to see what the patterns are. And if let's go to day 7. And you can just this slider bar to get to day 7. Day 7. Sorry. Okay, and you can see in day 7 here that the two members are showing a 29% variance versus a 19% variance. You can see the anomaly out here over British Columbia is a lot stronger in I guess it's a negative, positive value. But in the EFO2, you notice that the variability is down in the around the Gulf of California. And then there's there's also a low, what do you say, more negative values over the Ohio Valley. So that's what we can see there. So that's kind of giving us what the two most variable products are. So let's go to the cluster space page that we saw before, and we can see how they line up. And I haven't looked at this. I can see a lot of 4s up here, positive, positive in cluster 4. But remember, that's going to have less variability. 1, a lot of 1s here, which means that the second ensemble, it matches better with that second EOF here, and the reds and the blues, I see Canadian and European. Notice the GFS is, I see a lot of the second ones where we saw that minimum over the Ohio Valley. I mean, you can go around, but that kind of gives you an idea. And notice that's negative and positive. So it's positive in the first one, but it's showing some negative ones in the second EOF. Now, here's the anomalies. We'll go through there. You can see that. Now, remember I talked about that the impact for us in the East, this system out here in the Pacific and Atlantic may weigh heavily on this. So what you can do, if you notice the domains here, CONUS, and you can go to Eastern, and notice how that changes the calculations, and that may help you in your forecast. So we'll stay on that. We have one that just shows the differences instead of the anomalies. This is just plus or minus from the mean, which everything else is calculated off the mean. This one's just off the mean versus the 500 millibar, which is the can be off the reanalysis data. You can cluster your maximum temperatures here. We can do the East. Let's do the CONUS, see what the difference is. Let's look in cluster 4 down here. 17% of the members are similar to this one. And we're going to go CONUS and see what happens. And you can see that area is pretty much the western part, eastern part of the United States in that one. And we also have maximum temperatures, like I said, and then minimum temperatures. Notice this, remember this minimum temperatures is based off the average. So that's why this one does not have colors on it. And finally, the cluster QPF. And you can see here the values are more positive in cluster 1, and it's drier in cluster 2. I shouldn't say dire, it's less negative. I mean, more negative here than here. This is more positive, more negative in the QPF values. I can't say it's going to be more rain or less rain. It's all relative. So I almost fell into that. If you want to go back, this is based off the 0Z last night, and it's usually available about 12 hours after the fact. But you can go; they have go back the dates in the past. So I just wanted to show you that this is one tool that is fairly new. Offices I know in the Western, they mentioned Western Central region are using it, but this may be something that you want to look at for especially significant events that are coming up. It would be interesting to look in tropical, and also if we are lucky enough to get a weather event. So that's all I have. And Vicki, I'll turn it over to you.
All right. Anyone have any questions for Reed?
Just a quick comment, really quick, Vicki. Yeah, a lot of great resources there, Reed. Do you think we can add some of the links, especially this one you're showing now, the cluster prototype, if we haven't already, to the our Ensemble resource page in the Google site?
That's where it is, Mark.
Okay, perfect. Thanks, Reed.
Let me go back here.
Yeah, this stuff is great.
Back 1,000. I guess I didn't have it there. There it is, right here. Recent, okay, it's right there, awesome. Sir. Yeah.
Thanks.
Okay.
All right. So yeah, I guess that'll probably be something that we'll learn more as we use it more. Because I know for me it was a lot to take in. So look forward to keeping an eye on it.
It's difficult. It's new, and I think it's exciting stuff to look at. And We'll see how well it does at day 3 versus day 7, because I know when Jim Nelson and those folks at WPC started looking at it, they were looking at days 8 and 10. So.
And those aren't available online, right?
Yes, that's available. Yeah. Oh, 8 and 10? No, I don't see
No.
those anymore. So they just have gone to 3 to 7.
Okay.
If you look at their GUI, I see days 8 to 10, but there's no link to it. So they must have stopped doing it.